especially as we're trying to build these error-corrected intermediate scale quantum computers. There's a lot of excitement that quantum computing will be useful for society. However, there's a big elephant in the room, and the elephant is we don't know if we could use a NISQ computer, but rather we will likely need an error-corrected quantum computer for useful applications. So today, and the problem with that is that it's very hard and the timelines are not well known. Today, I'm very excited to talk about our roadmap to build an error-corrected quantum computer in 10 years, and I'm more excited to introduce the team leads who will be doing this. They will be going through the concrete milestones that we have for building an error-corrected quantum computer, and they will be also talking about what they can do, what the community can do to help us in this very challenging endeavor. My name is Alan Ho. I lead our product management and program management, and I'm happy to moderate this panel. To give some context, we're embarking on two grand experiments. The first experiment is to use our current quantum computers that we have today to discover useful applications. And below here is the first computer that was able to do a beyond classical computation, namely our Sycamore processor. Our second big experiment is to build an error-corrected quantum computer in 10 years, and the schematic you see below is a quantum computer at scale. And we've developed a set of hardware roadmap milestones that are specific to building an error-corrected quantum computer. We first start with building a logical error, a prototype, followed by building an actual qubit, followed by a gate, at which that point we believe most of the physics is de-risked, and then we're going to scale up to build that quantum computer. But to do this is going to be very challenging. So we've had 3 new team leads at Google who is endeavoring on this this big challenge. And they've been working together since the time that they were in John Martinez's group for 10 years. And they've been taking lead positions at Google for over 6 years. So with that, I'd like to introduce the team. So Anthony, can you kick us off to introduce the team?
Thank you, Alan. So I'm Anthony Megrant. I am a research scientist at Google since 2015, and I lead the devices team. I started in quantum computing back in 2009 when I joined Andrew Cleland's group, where I focused on understanding and improving the materials that we use to build our superconducting quantum computers. My original intention, actually, when I joined grad school, was to work in alternative energy to help global climate change. However, once I learned about Andrew Cleland and John Martinez's work over in the physics department, I realized that that was definitely the right choice for me, and I haven't looked back since.
All right, and Julian?
Great. Hey everyone, I'm Julian Kelly. I've been at Google for about 6 years now, but actually started in quantum computing at 2008 as an undergraduate. And my first project was actually on single qubit gate calibration and phase qubits, and I also did some randomized benchmarking. And I really got hooked in quantum computing when I realized that it just wasn't nearly as abstract as how they teach quantum mechanics to you in, say, undergraduate or graduate school, where you're looking at all the math and you see these emergent physics phenomena. But when you're actually like in the lab interfacing with a qubit and you can just do very dynamic things with it, I just got hooked, and then I couldn't stop.
Yeah. So, hi everybody. My name is Yu. I actually have a slightly different trajectory into this field compared with Tony and Julian. I did my PhD in a completely different field. It's condensed matter physics, focused on quantum phase transition. And in 2010, I decided to move to quantum computing. Because at that moment, I got a feeling this is an exciting field. I'm not sure. And afterwards, I feel I actually almost got my second PhD because there's a lot of things to learn and a lot of training to go through. Of course, at the beginning, there's a lot of frustration, as you can imagine. However, if you look back, when I look back, I feel this is probably the most important decision I have made so far for my professional career. And so far, it still looks pretty good. So my take home is basically don't be afraid making changes in your life.
All right. So Anthony, tell me a little bit more about the devices that you're making.
Yeah, happy to. So my team focuses on the device aspects of building a quantum computer, specifically improving their performance and the scalability. So in the upper left, you'll see the Sycamore quantum processor that we use to achieve beyond classical computation that you mentioned in last year. we design and we fabricate these devices. And the materials that we use are actually quite similar to conventional integrated circuits. So in the middle panel, in the upper middle panel, you'll see aluminum traces in a scanning electron microscope. Um, and these aluminum traces are very similar to the integrated circuits that might be in your cell phone. However, what you might notice if you look really closely is there's nothing supporting those traces. The dielectrics have been removed as they degrade the performance of our device. It is these little tricks that we've had to learn to benefit the performance of our device and to achieve the quality that went into the Sycamore processor. Additionally, my team focuses on building the peripheral components around the processor, such as the amplifiers that allow us to read out our qubit signals at the quantum limit. And the packaging that the processors and the amplifiers are placed in that include the shielding that protects our devices from the external environment, and also allows the control wiring to lead into the processor itself. Speaking of control wiring, you can see that in the right image, which is a picture of our dilution refrigerator of our Sycamore processor. And you can barely make out the packaging of the Sycamore processor if you look really closely down at the bottom. However, what's dominating that image is the control wiring. And that's another aspect that my team works on, where we're focusing on trying to build out the next generation of much higher density control wiring in collaboration with the metrology team in Chen.
How about, I would love to learn a little bit more about the system control team. So what do you guys do for system control?
Thanks, Alan. So what Tony talked about, he talked about the processor and all the wires that go to it, but how do we actually use that to perform computations? So the team that I lead is responsible for the software and the hardware control system in order to do that. So something that's really important to appreciate about quantum computing is that control is really a large challenge, and that's because control of quantum systems is inherently analog, and we have to individually tune this control for all the different quantum elements. On top of that, learning these control parameters is hard because it actually has to be done in situ. So what we do is we use machine learning and AI techniques to write algorithms that allow us to learn these control parameters and then optimize the system performance. On top of that, our team also builds a software layer, which we call Quantum OS, that helps us turn circuits, say circuits that people want to use to run experiments, and we turn that into waveforms that we can then schedule in our control electronics. We then pass this information to the control electronics, and they make these shaped voltage and current pulses that go to manipulate the qubits themselves and also read out their quantum states. And then additionally, we're doing work on ASIC development for the future of scalability in terms of price, performance, and footprint. And then lastly, we've also been working on a number of error correction experiments recently.
Cool. And you, Chen, can you tell us a little bit? People don't know what metrology really means, so do you mind kind of enlightening us a little bit about that too?
Yeah, absolutely. So Julian and Tony basically show you almost a full stack of the technology we've been working with. The team I'm working with is called Metrology. You can think about this basically it's like R&D team inside this research project under Google Research. So I usually call this team like triple R team. So the goal of this team is basically trying to gain fundamental understanding of the system and also develop metrology tools as well techniques such that we can improve the performance of the system. So the keyword here basically the performance. And this performance basically means how can we achieve high performance on the algorithm, no matter it's for error correction or it's for NISQ algorithm. And this translated into two aspects. It translates to component performance, that's the one I showed you on the left. That means high fidelity gate or high fidelity radar. It also translates into high performing hardware. In this case, we're focusing on cryogenic system. In this case, in the cryogenic system, basically we need to build a system with high cooling power as well as large space. And this system we use as a foundation system, such that we house every other item and every other component inside the system. When all those development get done and with high performance, they come back and rewarded by the high performance algorithm, like the one I show you in the bottom middle panel. Basically, you can think about this as an algorithm we run. We have detect strong enough signal even after we have run thousands of single qubit gate and hundreds of qubit gate. And this is something we have done right now in the lab. And also this is something we have demonstrated in the past in our experiment in 2019.
Cool. So Julian, why don't you tell us a little bit about the first milestone, this logical qubit prototype milestone?
Yeah, thanks, Ellen. Happy to. So I want to talk just a little bit of context about our path towards building an error-corrected machine. And the first thing to really appreciate, and that's foundational to all of quantum computing, is that the qubits are inherently error-prone. So if you think that you're trying to get a lot of qubits together, run a really large algorithm, you're going to get overwhelmed with errors. So there's a solution to this, which is error correction. And we all kind of believe that the end game for quantum computing is to build error-corrected machines. So at Google, our approach is to use the surface code error correction scheme with transmon qubits. And so the way that we understand our trajectory is we like to look at this 2D phase diagram where we both look at the number of qubits in the systems that we like to build along with the limiting error rates. And so you can see on there for reference, we have our recent beyond classical computing demonstration where we show that we can run an algorithm better than a classical computer for the first time. In the bottom right, we have this future fault-tolerant error-corrected quantum computer that we eventually want to get to. So what we've done is we've drawn out this trajectory that we'd like to follow, and then we've annotated these particular stars, which are the milestones along that path. And so what I first want to talk about is this upcoming milestone that I've circled there. And this is essentially a foundational error correction milestone. And so the way quantum error correction works is that we use a collection of physical qubits to make a logical qubit. And then as we continue to add more physical qubits to that logical qubit, we can actually suppress the errors. So this foundational demonstration is basically to show that if we make a smaller logical qubit and compare it to a larger logical qubit, the larger logical qubit actually has a reduced error rate, or more qubits gives us less errors. What this means is that we can actually establish a path to make a system significantly larger and reduce the errors arbitrarily to the point where we can perform large algorithms.
Cool. And Anthony, can you like kind of explain to me what's like our end state that we want to be at?
Yeah, so actually, in our road mapping process, like Julian just outlined and how you described it in the beginning, we actually started with our end goal in mind, which is to build 1,000 logical qubit quantum computer. And from what we understand today, that'll be around 1 million physical qubits. This is very far from the 100 qubit systems that currently exist. And one of the outcomes of our entire road mapping effort is this system level drawing that you see here. And what I want you to take away from this is a very large but self-contained system. So there's a human figure there for scale, where you can really see the size aspect of this quantum computer. We designed our final system with modularity in mind. And this allowed us to develop the milestones that you heard about earlier and allowed us for very early testing so that we know if we're on the right path. And if we're not, we can get back on that correct path as soon as possible. So the modularity aspect here is there's a few logical qubits per each one of these modules. And there's roughly 100 modules or so for the 1,000 qubit total qubit quantum computer system. One of the things we identified very early on, and I kind of highlighted earlier when I described my team, is the requirement for fan out to get all of the control wiring in to individually control our qubits. And so what we came up with to deal with that is a semi-linear scaling solution that you see here as it goes off into the distance. Once we had a rough understanding of the 1 million qubit system, we then set out our roadmap and specific milestones to address these outstanding questions and challenges that we would have to actually go and build this thing.
So maybe just a roundtable question, like what do you guys see from your perspective as the biggest challenge for making this happen?
Yeah, I can go ahead and start that. Well, as the road mapping effort definitely illuminated that there's many challenges toward building a fault-tolerant quantum computer. And that, like I mentioned, we used the roadmap to try to address these challenges as soon as possible so that we would know that we're on the right path. And maybe I can give an example of that in a little bit more detail with the first two milestones, where we're really focusing on proving the system performance of our processor. Where the first one, we're actually improving it enough to demonstrate quantum error correction, complete quantum error correction for the first time. And then the second milestone is where we can now show arbitrarily low logical error rates and fast decoding so that we can actually decode the errors as they're happening in real time. Once we've achieved both of these milestones, we've largely de-risked the physics associated with quantum error correction.
Yeah, so to kind of piggyback off of that, I mean, once we've achieved these two milestones that show that quantum error correction works, we're left with a very large engineering challenge. And a lot of that has to do with essentially the scale of the control system, the electronics that we have to build, the wires that we have to get into the fridge, the fact that we have to use individual calibration on all the qubits. All of these things are very much on our minds. And in addition to that, as we're building these systems in order to get the performance that we need for the near-term milestones, we really need to be thinking about how that translates into large scale. So we need to be building things that are modular in a way that we can build, go up to very large systems and nothing, say, too bespoke.
Yeah. So maybe I can follow up on that. Because to me, the biggest challenge is we have just too many challenges, and from high fidelity gate all the way to high precision control. And the biggest problem is all these things need to work all at once. Because the final system we build is going to be, as Tony said, it's a large facility, it's very large, with tens of millions parts all inside. We cannot build like 10 systems and choose which one is the best and then go with it. So all we have to do is build one system and make sure everything works well. And then this is where we need to basically introduce this important concept. We require high reliability on this system. Every part we build cannot only work once, need to work all the time, and need to work on billions, maybe tens of millions of parts. So this basically is a big transition or mindset when we transfer from academic group to this industry effort. And this is actually also important because this has to be a persistent effort throughout the entire road.
Okay, well, sounds like it's really tough. And so, how do you guys manage to not kill each other when you're working on these really hard tasks?
Well, that is absolutely hard, and I agree. And so another aspect, so to get this final system to work, as I said, those many parts need to work all at once. This also requires the entire team to work well with each other all at once. So this is tough, and luckily, and I think all of us have been really working with each other for more than 10 years. And it's very lucky to have such a talented team and with all these people working with each other. So of course we fight against each other on the technical merit. We had a lot of like parking lot working around to share thought with each other on in our life, in our technical work. And then through those interactions, you kind of learn how to work with each other, adapt to their working style. I can give you a lot of tips how to work with Julian, how to work with Tony. For example, if you really want to not having a 3-hour conversation with Tony, just schedule a meeting at 5 o'clock in the afternoon, and then he will go home at 6, and you end up a 1 hour discussion with him.
Yeah, to follow up on that, I really think just the best thing about our team is it's how talented everyone is, and a lot of us go back many years, like what you was just saying, and Tony and you, Chen, and myself go back about 10 years, and I just think about some of the interactions I had with them back in the day, like the very first qubit that I ever fabricated, I used Yu Chen's design in his mask set. Tony grew the wafers that I needed for my PhD project to execute these systems and demonstrate these algorithms. And that really is just great to lean back on that rapport when we have these technical disagreements.
Yeah, as you, Chen, and Julian just mentioned, we've been together a long time, and many members of the team have been around for around 10 years. We've had a lot of late nights and shared meals. We have very fond memories of Yu Chen ordering authentic Chinese food for the entire team, really commanding the restaurant and bringing all these amazing dishes out. And one of the things that I really like about Yu Chen is his unique description of how food tastes. Yu describes everything that's spicy, that's not spicy, as sweet. So you can picture us arguing at one of these late night dinners about how sweet a cheeseburger actually is.
Yeah,
Well,
that's absolutely true.
I'm glad that since Julian was able to depend on you, Anthony, for delivering his PhD, hopefully you could deliver us an error-corrected quantum computer pretty soon too. Okay, so maybe last question, Yu Chen. What if we're wrong? What if this is not? What if the surface code and transmon is not the right solution?
Wow, that is definitely possible. Because I think not just for us, it's for the entire community, the biggest challenge to build a quantum computer is that unique forward is not, oh, sorry, the path forward is not unique. We don't really know what's the optimal path forward. Right now, I think we just choose transmon based on surface code. There's no guarantee this is optimal. That's why in Google, we're always looking out for alternative solutions. We're looking at many random efforts, no matter it's different types of qubit design or different error correction code. By looking at those different things, and we can always reflect ourselves what is where and where is the optimal path for us to take forward. So this is actually the area we think we can actually work with well with academic group as well as the rest of the community. And this is also the way we feel we can actually engage with the community to tackle those extremely hard, difficult problems.
Okay, well, that's a great call for action. So I would like to, if you guys want to learn more, please Google Quantum AI. Check out our new website where you get to see our best, newest research as well as some of our tools. And thank you, the hardware team leads, Julian, you, and Anthony, for your time. And take care.
Thank you.
Thanks,
Thank
Alan.
you.